Hello, welcome to another module in this massive open online course. So, we are looking at M-ary PAM, that is M-ary pulse amplitude modulation, okay, and we have looked at the optimal decision rules for M-ary PAM. That is the set of cases, optimal decision rules, and what we have seen is the following thing. For instance, for all interior points A, for all the interior points we use the nearest neighbor rule. That is, if RT lies between in this region, that is 0, which is the midpoint of minus a comma a, or 2a, which is the midpoint of a comma 3a. If it lies in this region, that is, if RT lies in this region, the decision should be basically that A naught, the decision is that A naught is equal to A, this is the decision, and so on. We have also called this as the nearest neighbor decision rule. This is your nearest neighbor decision rule, that is A naught equals closest neighbor the closest neighbor of RT. Okay, this is the nearest neighbor decision. Similarly, if it lies between 2a, RT lies between 2a and 4a, in this region the decision is A naught equals 3a, that is the symbol or the level 3 has been transmitted. Okay. Now, at the end point something interesting happens. When you look at the end point, now there are two end points, one corresponds to, there are two end points. This corresponds to, of course, 2i plus 1 times a, where I equals m by 2. Remember, I lies in the range 0 to m by 2. So, this is equal to 2 m by 2, I am sorry, I is equal to m by 2 minus 1, correct, 0 less than or equal to I less than or equal to m by 2 minus 1. So, the maximum value that I can take, I think we should have illustrated it here, yeah, 0 less than or equal to I less than or equal to m by 2 minus 1. So, I is equal to m by 2 minus 1, corresponding to that this will be 2 m by 2 minus 1, that is 2 m minus 2 plus 1. So, this will be 2 m, so this will be m minus 1. So, this will be, so let me just write this over here, this will be m minus 1a. Similarly, this is minus 2i plus 1a, corresponding I equal to m by 2 minus 1, this is equal to minus m minus 1a. And these are the 2 points which we are calling it as the end points. These are the end points. One of them is m minus 1a, the other is minus m minus 1a. Now, of course, the next point here will be m minus 3a, here it will be minus m minus 3 times a. Now, if you look at the midpoint of this, the midpoint of this will be m minus, this midpoint will be m minus 2a, and this midpoint will be minus m minus 2a. So, if RT, remember there is no point to the right of this end point. So, if RT lies anywhere in this region, then decision is A naught is equal to m minus 1 a. Similarly, since there is no point to the left of this, if R t lies anywhere in this region, that is less than minus m minus 2 a, if R t lies in this region, then the decision is a naught is equal to minus m minus 1 a. So, the final set of decision rules will be R t greater than or equal to, let us just write it consistently, if R t is less than or equal to 4 a. Here, just to be consistent, we cannot write equal to at both the places. So, just to be consistent, let us write this as if R t is if or let us write it as this way, if R t is less than 2 a, 0 less than or equal to R t. Okay, let us write inequality only on one side, because if at, although it is not a very significant thing, because if R t equal to 2 a, then we have to decide what do we have to choose. If R t equal to 2 a, do we choose a naught equal to a, or should we choose a naught is equal to 3 a? What we are saying is that point 2 a, let us choose a naught is equal to 3 a. Okay, so 2 a less than or equal to R t less than 4 a. Okay, so minus 2 a less than or equal to R t less than 0. R t equal to 0, we are choosing a. R t equal to 2 a, we are choosing 3 a. R t equal to minus 2 a, we are choosing minus a, and so on. Okay, just to avoid that ambiguity at the boundary. Okay. Now, so therefore, what we can say is, if R t is greater, to be consistent in the spirit of consistency, if R t is greater than or equal to m minus 1 a, your decision R t is greater than or equal to m minus 2 a. In fact, that is the midpoint. R t is greater than or equal to m minus 2 a. The decision is a naught equals m minus 1 a. And similarly, if R t is less than minus m minus 2 a, then decision a naught equals minus m minus 1 a. So, this together with the previous cases completes. So, together with the previous cases, remember it has to be seen in totality, together with your previous cases completes the set of the decision. So, together with the previous cases, by the previous cases I mean this, for the central points. Okay, that is for this, these are for the, let us call these are for the, so the internal points. Okay. Internal points means a point which has 2 points, that is 1 point on either side. Okay, because these points in M-ary PAM, these are arranged on a line. Some points are the internal points which have 1 point on either side. Then there are the extremities, one towards the extreme right, which has only points towards the left and no point on the right, and one towards the extreme left, which has points only on the right and no point on the left. These points are respectively m minus 1 a and minus m minus 1 a. That is what we have seen. Okay. And the corresponding decision rules are, that is, if R t is greater than or equal to m minus 2 a, then we decide a naught equal to m minus 1 a. If R t is less than minus m minus 2 a, decide a naught is equal to minus m minus 1 a. Okay. Now, these are the complete. Now, what is the probability of error? That is the next question that we wanted to look at. We want to ask this question, what is the probability of error for this M-ary PAM modulation? What is the associated probability of error? Now, consider the transmission of A naught equal to A. Okay, let us look at this point. A naught equal to A, we have the next point 3A minus A and so on. So, consider the transmission now. Error occurs if the received, see, because if RT is less than, if RT, so if RT is less than, so decide A naught equal to A if, well, if 0 less than or equal to RT less than 2A. So, if RT lies in this interval 0 to 2A, we are deciding that A naught is equal to A. Therefore, error occurs if either RT is greater than, so observe that if RT lies in this interval, consider the transmission of A naught equal to A, if the received that is the RT, that is after match filtering and sampling, the statistic RT, if it lies in 0 to 2A, then there is no problem because we are deciding A naught equal to A. However, if RT is either greater than 2A or less than 0, then it will be mapped to some other point, and in which case we will have a symbol error. Okay. So, error occurs if RT is either greater than 2A or less than 0. Okay. So, let us note this. So, error occurs if RT is greater than equal to 2A or RT is less than 0. So, therefore, probability of error, now probability of error equals simply the probability RT is less than, well, RT is less than 0. Let me write it, be a bit more specific, because this is the union RT is greater than or equal to 2A. Union, because there is an error in case of I. So, if we call this event as event A, if we call this let us not call it A and B, if this call this event as event phi 1, this as event phi 2, then probability of error is basically probability of phi 1 union phi 2, where phi 1 denotes the event that RT is less than 0, phi 2 denotes the event RT is greater than or equal to 2A. And remember, these are two disjoint events, because if RT is less than 0, then it cannot be greater than or equal to 2A. Similarly, if RT is greater than or equal to 2A, it cannot be less than 0. So, these are disjoint events. Okay. So, these two events, these are disjoint events. Disjoint events means these are mutually exclusive events. Actually, these are, the correct term for this is mutually exclusive, not disjoint. Okay. So, probability of phi 1 union phi 2, from knowledge of probability and random process, which is again very important, as I have said many times before, is equal to probability of phi 1 plus probability of phi 2. Therefore, this is equal to the probability of error P is equal to probability of phi 1, which is the probability that RT is less than 0, plus probability of RT being greater than or equal to 2A. So, this is the net probability of error. Okay. This is the expression for the, remember, this is the expression for the probability of error. Okay. Now, what is RT? Remember, we have derived the expression for RT. RT equals A naught plus n tilde, A naught plus n tilde is Gaussian similar to BPSK, mean equal to 0, variance equals n naught by 2. Now, therefore, error occurs if either RT greater than 2A, RT greater than or equal to 2A, this implies A naught. Remember, A naught is A because we are considering the transmission of A, which means A plus n tilde is greater than or equal to 2A, which implies n tilde is greater than or equal to A. So, first scenario is error occurs if n tilde is greater than or equal to A, or R tilde or RT is less than 0, which means A plus n tilde is less than 0, which implies n tilde is less than minus A. So, error occurs if either n tilde is greater than A or n tilde is less than minus A. So, error occurs considering transmission of A naught equal to A if n tilde is greater than or equal to A or n tilde is less than minus A. Okay. Now, what is the probability that n tilde is? So, probability of error equals P, as we have seen these are disjoint events, equals P of n tilde greater than equal to A plus probability n tilde less than minus A. Okay. Now, if you look at n tilde is a Gaussian, correct? N tilde is a Gaussian with mean 0, which means it has a symmetric PDF about 0. So, mean equal to 0 implies PDF is symmetric about 0. Gaussian PDF is symmetric about the mean, which is 0. Therefore, the probability, now if you can look at any threshold A, the probability that n tilde is greater than or equal to A is the Gaussian tail probability greater than or equal to A. Similarly, if you can look at the probability that n tilde is less than or equal to minus A, that is the left tail probability, correct. And you can see by symmetry these two probabilities are equal. So, by symmetry, or you can also say, you can also see the same thing by symmetry. You can see by symmetry these two tail probabilities are equal, okay, by symmetry. Left and right tail probabilities. Left and right tail probabilities the left and right tail probabilities are equal. Therefore, this implies that probability n tilde greater than or equal to A. Well, of course, I should not say they are exactly equal, because probability, because you have that one point A, but that probability is 0. So, probability, so I will write this is equal to probability n tilde less than minus A, and this is actually correct because that probability of that one point A is 0. Okay. So, this is basically follows by symmetry. And therefore, what we have is probability of error. If you are following the argument, the sequence of arguments that we have made, probability of error is probability n tilde is probability RT greater than equal to 2a plus probability RT less than 0, which is equivalent to, which is equal to probability n tilde greater than or equal to a plus probability n tilde less than minus a, and we are saying that probability n tilde greater than equal to 2 greater than equal to a is same as the probability n tilde less than minus a by symmetry. Therefore, probability of error is simply twice the probability that n tilde is greater than or equal to a, okay, by symmetry. So, probability of error is simply twice the probability that n tilde is greater than a, okay, where n tilde is 0 mean Gaussian variance eta naught by 2. And now we have done from BPSK, we know that probability n tilde greater than a is q square root of a square divided by n naught by 2. This is q of, which is equal to basically q of n naught by 2 equals variance, which is sigma square. So, this is q of a divided by sigma. So, this is q of twice q of square root of a square divided by n naught. There is also another way to see this, because if you look at probability of n tilde twice probability of n tilde greater than a, or rather greater than equal to a, it is one and the same thing, greater than a or greater than or equal to a. This is equal to, I can write this as twice probability of n tilde over sigma greater than n tilde over sigma greater than a over sigma. And now, once I divide n tilde divided by sigma, n tilde is 0 mean variance sigma, you divide by sigma, you see n tilde by sigma is a standard Gaussian, that is with mean equal to 0, mean equal to 0, variance equal to 1. So, probability that standard Gaussian is greater than a over sigma, this is equal to q of a over sigma, because q of x, remember q of x equals probability standard Gaussian random variable mean of 0 variance 1 is greater than or equal to x, that is the definition from the very definition of the q function. So, anyhow, for an internal point, it follows that the probability of error equals twice q square root of a square divided by n naught by 2. Remember, but remember, this is only for an internal point, any internal point. Now, consider an external point, or consider a points end points. Now, consider for instance end points m minus 1 a, m minus 3 a, the threshold is m minus 2 a. So, this is one of the end points. So, consider the transmission of m minus 1 a. So, let us say we consider transmission of m minus 1 a . Consider the transmission of m minus 1 a. Alright, we are considering the transmission of one of the end points of the constellation, that is m minus 1 a. You can similarly also consider minus m minus 1 a, it does not make any difference. So, we are saying a naught equals m minus 1 a, implies R t equals a naught plus n tilde, that is equal to m minus 1 a plus n tilde. Remember, we decide R t equal to m minus 1 a if R t is greater than m minus 2 a. So, the error occurs if R t So, error if RT is less than m minus 2 a, that is m minus 1 a plus n tilde, error if m minus 1 a plus n tilde is less than m minus 2 a, we decide, okay, implies n tilde is less than, error if n tilde is less than m minus 2 a minus m minus 1 a, n tilde is less than minus a, okay. And by and therefore probability of error for the end point, for this end point, is the probability that n tilde less than minus a, which is equal to probability, again probability n tilde, because n tilde is symmetric, Gaussian noise 0 mean this is symmetric. So, by symmetry this is equal to probability n tilde is greater than a, this follows from symmetry. Which is equal to probability n tilde by sigma is greater than a over sigma. And now observe that n tilde over sigma, this is a standard Gaussian, probability that standard Gaussian is greater than a over sigma, this is equal to q of a over sigma. So, probability of error equals q of a over sigma. This is for the endpoints. So, we have probability of error for an internal point which is twice q of a over sigma, probability of error for an end point is only q of a over sigma, that is the difference. Now, assuming all the points are equiprobable, that is how many points do we have? Remember in M-ary PAM we have m levels, assuming all the levels are equiprobable, all of them each has probability 1 over m. Assuming all constellation points are equiprobable, assuming all constellation points are equiprobable, probability of, that is each point a naught is equal to any plus or minus 2i plus 1 a is equal to 1 by m. All points, there are m points, all points are equiprobable, implies that each point must have probability 1 over m, okay. So, now average probability of error, okay. So, because probability of error for end points and probability of error for internal points is different. Now, how many internal points are there? How many end points are there? There are 2 end points and m minus 2 internal points, okay. So, probability of an end point is 2 divided by m, 2 end points, 1 by m plus 1 by m. Probability that is an internal point is m minus 2 divided by m, okay. So, probability of end point equals 2 divided by m, probability of an internal point is equal to m minus 2 divided by m. Therefore, average probability of error, now you can see average probability of error equals probability that it is an end point 2 over m. Okay, let me write this a little bit more explicitly so that you get it clearly. Probability of error given end point into probability of end point, this is total probability rule, plus probability of error given internal point into probability of an internal point, okay. This is the rule of probability, okay. But this probability That is because end point and internal point are mutually exclusive and exhaustive events. This is something that you have to remember. Again, I urge you to look at the lectures for probability. These are mutually exclusive and also exhaustive. Anyway, so this is equal to probability of error given end. We have already calculated that is Q of A divided by sigma times probability of end point, that is 2 divided by m, plus probability of error given interior point twice Q of A divided by sigma into probability of interior point, that is m minus 2 divided by m. Now, this is equal to twice 2 plus 2m minus 2 divided by m q times a q of A over sigma, 2 plus, so this is twice 1 plus m minus 2, that is 1 minus, so twice 1 plus m minus 2, that is m minus 1 over m, that is 1 minus 1 over m q of A over sigma. This is the average probability of error, averaged over both the endpoints and internal points. Okay, this is the average probability of error. Now, all we have to do is we have to substitute A, expression for A and expression for sigma. Sigma is of course very simple, sigma square equals noise variance is n naught by 2 EP, EP is 1, so it is n naught by 2, which implies sigma equals square root of n naught by 2, and A, remember, if you remember A, it is if symbol energy equal to Es. A we have already derived very elaborately for the M-ary PAM. In fact, that was one of the first things that we derived. A is equal to square root of 6 Es by, oh no, I am sorry, A equal to square root of 3 Es divided by m square minus 1, where Es, remember Es is average symbol energy. So, average probability of error, substituting this expression for both A and n naught by 2, that is twice 1 minus 1 by m q square root of A square, which is 3 Es divided by n square minus 1 divided by n naught by 2. So, that will be 6 Es divided by n naught into m square minus 1. Okay. So, this is basically the average probability of error for M-ary PAM. It is slightly elaborate, but it is a very interesting derivation, and it is one of the fundamental expressions, because M-ary PAM is a very general digital modulation scheme. So, this is, let me describe a little bit more about it. Now, if you substitute m equal to 2, if you substitute m equal to 2, you can see that probability of error be twice 1 minus 1 over twice minus half is basically half, twice and 2 into half is 1. So, this reduces to q square root of, well, m square minus 1 is m equal to 2. So, m square minus 1 is 3. So, 6 divided by 3 is 2, twice Es by n naught, which is the same as what we had before. What we had before is Eb, q of square root of 2 Eb or n naught, but for 2 PAM, that is when m equal to 2, the average bit energy is the same as average symbol energy, because number of bits per symbol is 1. Alright, so average bit energy is the same as average symbol energy. Okay, and therefore, what you are seeing is we have derived the average bit energy for M-ary PAM. As I said, this is a very general modulation, because in M-ary PAM you can transmit log m to the base 2 bits per symbol. So, unlike the previous modulation schemes such as binary phase shift keying etc., you are not limited to 1 bit per symbol, you can load a larger number of bits on each symbol, and that is helpful especially in modern high speed wireless communication systems, because if you have a good channel where the SNR is good, you can keep loading a large number of bits on each symbol such as 4 PAM, 8 PAM, 128 PAM. In fact, we are going to see a much more general modulation scheme next, that is known as QAM, which is similar to QPSK, that is we have two basis functions and you can load any number of bits on each basis function, correct, each orthogonal basis function or each orthogonal basis signal. Thereby, by increasing the number of bits per symbol for the same symbol rate, you can significantly increase the bit rate, okay, and that is how one achieves higher and higher data rates, for instance in 4G wireless communication system, or now people are talking also about 5G wireless communication systems. So, by loading, by using higher, these are known as higher order modulations, by using higher values of m, by loading large number of bits on each symbol, one is able to achieve higher data rates. That is why the performance of this general modulation scheme is important, okay. So, by loading, so the final point I want to mention is number of bits, again emphasize number of bits per symbol equals log m to the base 2. By loading large number of bits per symbol, rather than simply 1 bit per symbol, losing large number of bits per symbol, one is able to achieve higher data rates in, for instance, 4G and 5G. So, these are very important, 4G and 5G. That is the whole point. Okay, so, this is something. So, this is basically summarizes the probability of error for M-ary PAM. Let me just write it over here so that it is clear. Probability of error for M-ary PAM. Okay. So, basically that wraps up this module, where we are in the previous module we have introduced M-ary PAM, partly discussed the decision rules for the internal points. Now, we have completed the discussion regarding the decision rules for the endpoints. There are two endpoints, okay, and what is the probability of error for each point, if it is an internal point, probability of error for an endpoint, and therefore, what is the average probability of error, and we have derived an expression for that. Okay, all right. So, please go through this derivation again, because it involves several steps, a series of logical arguments that we have to make and a series of computations that we have to make at every step, and we have used several different properties, such as properties of random variables, such as properties of mutually exclusive events, properties of mutually exclusive and exhaustive events, the total probability rule, etc. So, this is a very interesting derivation that also, that of course tells you what is the average probability of error, what is the optimal decision rule, what is an M-ary PAM constellation, what is optimal decision rule, what is the resulting probability of error, and also explains or gives or better, or also this practical example helps you better understand several principles of probability and random process. Alright. So, we will stop here, we will look at other aspects in the subsequent modules. Thank you very much.